how to write the uh, molecular orbital diagrams and what is the concept behind it, and how do we arrange the electrons, how do we calculate the bond order based on it, and what happens when a diatomic molecule gets ionized, whether it gets accepts electron or loses an electron, what happens to the bond order. And we, I think, went through a lot of stuff, right? Were there any questions on that? Because clearly that will be part of your second exam. Anything that's not clear before we continue on with what we call the molecular symmetry? Can you all see the board, folks? Yeah. Are there any questions? Because I don't want you to come back and say, oh, I didn't know. I don't understand the molecular orbital pictures, the day before the exam. That's not a good way of learning. I think we know this already.
I was kind of confused on just when you draw like each of the atoms over here, and then when they go up and down to the antibonding and bonding. So I was just kind of confused. If you can go over that one more time.
Sure. We'll go with a simple one like hydrogen 1s orbital, right? So why one goes down, why goes up, right? That's the confusion that you have. All right. So it's natural to have that. So let's assume that we have two hydrogen atoms, okay? Hydrogen A and hydrogen atom B, each with one electron, right? So now the way it happens is these electrons happen to be in s orbital, which is spherical in nature, correct? Can you all see that? Now, in spherical orbitals, both the electronic wave functions, you remember electron moves, right? When the electron moves, it creates a wave. Now, the question we're trying to answer is, are the waves that you see in hydrogen atom A and hydrogen atom B, are they in phase or out of phase? If they are in phase, they are going to form what we call a lower energy bonding orbital. If they are out of phase, they create a high energy orbital, which we call antibonding. So this is more like adding the wave functions of hydrogen A and the wave functions of the hydrogen B. On the top, it is the difference in the wave functions of A and B. A difference in the sense they are out of phase. Okay. So usually what happens is if they are in phase, the wave functions are shown as plus plus here. Just give me 1 second. People are joining. And on the other hand, if you have an anti-bonding, it is plus and minus. They're out of phase. They're off by 90 degrees. Okay. So one thing that we have to keep in mind is before the formation of molecular orbitals, we have certain energy with both these electrons, right? Now, when you lower the energy of one, you have to also increase the energy so that the net energy is zero, because energy cannot be created nor destroyed. So that is the formation, that is the philosophy behind the formation of molecular orbitals using atomic orbitals. In a scientifically fancy word, we say this is a linear combination of atomic orbitals. Now, these atomic orbitals come from two different atoms, not within the same atom. That is the big difference between hybridization and molecular orbital. In hybridization, we use the atomic orbitals within the atom, but in molecular orbital theory, we use the atomic orbitals between atoms. Does that make sense to you?
Yeah, so then you just have one electron on the antibonding and one on the bonding?
No, what happens is if I have two electrons, right, each level, according to Pauli's exclusion principle, can hold two electrons, correct? So if I have only two electrons, then both the electrons will go down and there will be nothing in the anti-bonding level.
Okay, right. And so it's just the bonding.
Yeah. So which means there is a strong bond between these atoms, and the bond order in this case is number of electrons in the bonding orbital minus the number of electrons in the antibonding orbitals, and
Right.
take 1/2 of that,
Right. So it's just one.
just one.
Okay.
On the other hand, if I were to have helium, right? Now helium has, each helium atom has 2 electrons, right?
Right.
Now when you make this bond, now what we have now here is, we have 2 electrons in the bonding, and we have to place 2 electrons in the antibonding level for the helium too.
So now it's a 0 bond order.
That's been 0 bond order. That is true too. In helium gas, it's always monoatomic. You never see diatomic gas.
Okay. Thank you.
That makes sense? Yeah. So follow my lecture again, and if there are any questions, please ask me for a private web conference and we can talk about it. That goes to all of you. All right, I'm willing to even talk to you on a Friday or Saturday. You know, I don't care. As long as I don't want you to fall behind learning the material. That's the worst thing that you can do to yourself. Not learning the material on time and trying to cram everything the day before the exam, and you know, it doesn't work. We talked about this many times before. Okay, folks. So that now leads us to the concept of what we call symmetry. It's a very important topic in both PChem as well as in inorganic chemistry. Now, symmetry, we all have an idea, right? Suppose if I draw something like this and something like this, two objects, objects A and B, right? What do you think? Which one is more symmetric, object A or object B?
B.
Okay.
B, right? I mean, we are, you know, wired internally to identify and then say which is symmetric and which is not symmetric, right? But that is a very qualitative understanding. But that is not enough for the science. So we need to have what we call a quantitative understanding of what symmetry is in molecules. Suppose if I were to show you a molecule of water, right? I'm holding a molecule of water. As you can see, I have an oxygen and 2 hydrogens on it. It's a V-shaped molecule. We all know this, right? So this has its own symmetry elements. On the other hand, if I were to hold a methane molecule, which is tetrahedral, can you all see this? Right? This seems to have more symmetry than a simple one like this. Now, if I look at a linear molecule, something like this, it's even more symmetric. So how do we assess which one is more symmetric, not just qualitatively, but quantitatively, right? So the question oftentimes comes to our mind is, so what can we learn from understanding the symmetry of molecules? As you go to advanced classes in graduate or other classes, you will find symmetry makes your life very simple in terms of interpreting the electronic spectra or understanding the polarity of molecules, which ones are polar, which ones are not polar. And it also tells you what type of vibrations are allowed in a molecule. So if you now think about this, this is a big deal because on one hand, you're looking at the electronic spectra, right, which happens in the ultraviolet region. And when you're talking about vibrations, you're talking about infrared spectra. So the entire spectroscopy between UV visible to IR, if you want to predict the properties and spectral properties and model them, you need to understand their symmetry. Similarly, when you extend the molecular symmetry to solids, then you get into what we call a band theory, which helps us predict even the properties of solids. Why is copper a metal? Why is silicon a semiconductor, right? All these are related to the symmetry of the electronic wave functions. So we have used the word symmetry many times. Something is symmetric, something is asymmetric, something does not have symmetry elements. So we need to develop what we call a language that will help us understand the meaning and how do we systematically approach the topic of symmetry. Before we continue, I just want to make sure, Mr. Gurveer, are you recording this?
Yes, I am.
Okay, thank you very much. So after this is done, those of you who could not come to the class can always watch this video later on at their convenience. Okay, let's look at, there are two important terms that we use, and oftentimes students get confused between them because the words look very similar. One is called symmetry operation, and the other one is called symmetry element. Okay, now these two are totally two different things, but oftentimes students get mixed up between these two terms. So let me define this for you. A symmetry operation is an action such as rotation, reflection, or inversion that brings the object into an apparently unchanged state. Watch my language very carefully. I mean, when you do these operations, and if the molecule looks as if nothing happened to it, it looks exactly same as before, then we say that's a symmetry operation. On the other hand, symmetry element is a geometric entity such as a line or a plane or a point with respect to which a symmetry operation is carried out. Okay, so symmetry elements are generally geometric quantities. It could be a line, a rotational axis, or it could be a reflecting plane or inversion center. These are all the languages. Of course, we are going to give lots of examples to convince you that there is a lot of stuff that goes on when you go into the depths. All right, so the main object, whether you're doing a symmetry element or a symmetry operation, is whatever you do to it, if the molecule remains apparently unchanged, that means it assumes a shape that is indistinguishable from the original shape. Or, if you like, you are creating a twin. They look identical. Although you have done something to this, but at the end of the operation, you get an object that looks exactly like what it was before. So let's look at a linear molecule like H2, right? Do you see that? Now what I can do is I can rotate this molecule right in the middle by 180 degrees and turn it around. Still hydrogen, right? If you closed your eyes when I was doing this and open your eyes after I finished doing the operation, would you be seeing any change? Right? Apparently it looks unchanged. I did something to this, but you will find it very difficult to believe that I did something to this because there is absolutely no change. In other words, the before and after, the shapes are indistinguishable. You cannot differentiate between those two shapes. As long as you achieve that, you can say, well, I have some symmetry element present here. Some molecules have more symmetry elements than other molecules. As we go through examples, you will find some have a great number of symmetry elements, some have very few. Okay, so to do that analysis, we need to understand exactly some language that we use. So we start with the most simplest one that is present in all objects, what we call E, or we call that identity. It is called an identity operation. Identity operation is similar to doing nothing. It may look silly, but this is a very important part of symmetry arguments. If I'm holding this molecule in my hand, and if I don't do anything, its shape will not change, right? I can hold this for infinite number of years and the shape remains the same. So doing nothing is what we call an identity operation, E. That is present in all shapes and all sizes. So you can take any object, like for example, this writing marker. If I don't do anything, it looks exactly the same. So all objects inherently have at least one symmetry element, that is E. Okay. it is mathematically saying that you are multiplying it by 1. Right? When you multiply anything by 1, or if you take the coordinates of all the atoms in this marker and do what we call unit operation by using a matrix, unit matrix, you get the result the same thing. It will be exactly identical because you're multiplying everything by 1. All right. So this is the identity operation. So we have to keep in mind that all molecules, regardless of their shape, regardless of their geometry, regardless of the bond angles, they all inherently have an identity operation. Okay, that's very simple to understand. The next one we need to understand is what we call rotational axis of symmetry. So rotational axis. The rotational axis is designated by the letter C and with a subscript n. C sub n. N can be 1, 2, 3, 4. N cannot be a fraction. N cannot be a negative number. Okay, those are the rules. So some molecules have C1, some molecules have C2, C3. So what exactly is the N? Here is the meaning of N. If you rotate the molecule through an axis by 360 divided by N, okay, and if the apparent shape of that object after this operation remains unchanged or apparently unchanged, we say the molecule has Cn axis of symmetry. So let's look at an example of a Cn axis of symmetry. So let's look at water, right? Here is the molecule, the central one, oxygen I'm holding, and these two are the hydrogens, okay? Now, suppose if I were to rotate this molecule along an axis, which I'm holding right here. If you can see, that is the axis here. If I rotate it by 180 degrees, what happens? The molecule now turns around and presents itself in a form that is indistinguishable from the previous form. Would you all agree? Right? So if you rotate this by 180 degrees, and if you get a form that is indistinguishable, what should be the n value here? Go back to the definition, right? What value of n will satisfy 180 degrees? One of you can answer?
2.
2. So we say water has a twofold axis of symmetry. So we have H and O, and that axis right here, when you rotate it by 180 degrees, you get a shape that looks exactly like the original shape. So we say water has a C2, twofold axis of rotation. You see the way I'm slowly changing my language. Watch me very carefully. I say water has a twofold rotational axis of symmetry, and I say that axis bisects the HOH angle, right? So that line is your symmetry element, and the operation that you're doing is a rotation. Again, I'm coming back to the basics of symmetry elements and symmetry operations. I will not be doing that as we go into more and more examples, but in the beginning, I thought it would be useful to distinguish and develop the language and use it very comfortably and accurately. So we have a symmetry element of rotational axis, C2, and the symmetry operation here is a rotation. All right, so let's look at some other molecules. Let's talk about a planar molecule, BH3, right? Now, does it have a C2? So to answer that question, suppose if I take the BH bond here as the line, and if you rotate this molecule with reference to that line by 180 degrees, what happens now? Let's say I'll call this HA, B, and C, 3 different hydrogen atoms in the molecule. When you rotate by a C2 along the BHA bond, so that means this bond here, when you rotate, you get HC here, HB there, HA remains the same. So this is a rotation along this, that is your C2 axis. Does it have any other rotational axis of symmetry besides C2? This is a planar molecule. So the angles here, what should be the angle here, folks? 120, right? So we have 120 degrees here. Now, watch me carefully. Suppose if I were to draw a perpendicular from the board and that line passing through boron, nothing else, right? And if I were to rotate that by 120 degrees, would I get a shape that looks indistinguishable from the previous one? Forget about the labeling of the atoms A, B, and C, because in reality, these atoms don't have any labels. I'm putting the labels only for our convenience. So if I were to rotate by 120, when I say 120, that is 360 divided by 3, right? So I say it's a C3. Now, if I were to rotate, what happens is I get a situation where the hydrogen A will go here, hydrogen C will go here, hydrogen B will come there. If you remove those subscripts A, B, and C, does the shape look exactly the same as before? Yes, it does, right? So we say this molecule also has a C3 rotational axis of symmetry. So we call this C31. You can also do the second one, the same rotation. If you do that, you get again the same shape. This time HA will go there, HC will go there, and HP will come here. You see the rotations I'm doing. Now, if I do one more rotation, C33, third rotation, I get exactly the same thing as before. So when I do C33, it is as if I haven't done anything to the molecule. What is that operation we call that? In the beginning, we talked about
Identity.
Identity. So that is your E. So if you do a threefold rotational axis of symmetry 3 times, then the resulting operation gives you a geometry as if nothing happened to the molecule, which is equivalent to identity operation. This is true for any CN operation. If you do CN n times, you get E. If it is a C2, right? Remember this C2 water molecule, right? If I do one, it rotates this way. If I do one more time, it comes back to the original shape, as if nothing has happened to the molecule. So C22 in the case of water is identity. Am I making sense? All right, so let's look at other geometries. Let's look at NH3. You all know NH3 has a pyramidal shape, right? We talked about that. So here is the shape of NH3. The nitrogen slightly elevated, 3 hydrogens on the plane. So if I put it on my palm, you can see the hydrogens are resting on my palm, but the nitrogen is not. So this is not a planar molecule. It is a pyramidal molecule, right? It's a trigonal pyramidal molecule with a triangular base with the nitrogen elevated above the plane of 3 hydrogen atoms, as you can see here. Those of you who have models, you can also create these models at home and play with them. I think those of you who have done organic may have some of the models already with you. All right, so the question then is, does it have any rotational axis of symmetry? So we have nitrogen. Is a lone pair. Does it have any rotational axis of symmetry?
Yes.
Yes, and what is the order of the rotation? Is it C2 or C3 or C4, C5? What does it have? To answer that question again, we have to see the picture here. All right, I'm now holding the ammonia molecule and I inserted a line here on the top, right? So let's start with this one here. Right. Suppose if I rotate this by 120 degrees, do you get identical shape? Right? If you rotate by another 120, again, you get an identical shape. So what should be the highest fold rotational axis of symmetry on this now? 120 degrees implies it should be a C3. So this is your C3. Does it make sense, folks? Right? Suppose if I have methane, CH4, what is the rotational axis of symmetry does it have? Again, it's like ammonia, right? Except that I have a stem on top of it. This is a tetrahedral molecule. As you can see, there's a stem. So if I were to rotate by 120 degrees along the CH bond, right, it looks similar. So can we say it has a C3? Right? So it has a C3. How many C3s does this molecule have?
4.
4 of them, because each CH bond is a C3 axis, right? Whether you hold the molecule this way, that way, or turn it this way, you do have the same thing, 4 CH3s or 4 C3s, each CH bond. Compare this with the BH3, which had only 1 C3, but 3 C2s. This one has 4 C3s. Am I making sense here, folks? Let's take another example. Suppose if I have a square planar complex, all atoms in the same line, PTCl4 minus 2. What does it have? What is the highest fold rotational axis of symmetry? Understand, these are all 90 degrees each. Unlike BH3, we had 120 degrees. In PTCl4, we have 90-degree bond angle. So, yes. Go ahead, Alisa.
No, I was just trying to say I think it's C4.
You have a C4. You're absolutely correct. That's pretty good. That C4 is a line that is perpendicular to the plane of the board. If you can see the way I'm using my marker here, that marker direction is C4. That C4 is perpendicular. It passes through only the platinum atom. It does not touch any of the chlorides. So that is your C4. What else rotational axisymmetry this guy has in addition to C4? Does it have a C2? So if you look at this bond here, right, Cl, PT, Cl, that line, if you rotate this entire molecule along that line by 180 degrees, you're going to replace the Cl with this Cl, that Cl goes there, and the resulting structure looks exactly the same. So it has a C2. It also has another C2. You can use this line here, right? That also can, by rotation of C2, so this is a C2, that's a C2. Unlike C4, which does not lie in the plane of the molecules, so far these C2s are in the plane of the molecule. Can you identify additional C2s in this molecule? I wrote 2. Do we have more? How about a line like this that bisects the angle between Cl, PT, Cl, right? If I rotate this molecule along that line by 180 degrees, these two pair of chlorines will go there, and that pair comes back here, and the resulting structure looks exactly the same, indistinguishable, right? So that's another C2. Similarly, if you draw another line here, that is another C2, because this time this top pair goes to bottom and the bottom pair goes up by 180 degrees rotation. So this molecule has C4 and 4 C2s. Am I making sense here, folks? Okay. In general, molecules that have Cn and n number of C2s, that means it's a C4 and 4 C2s, or a C3 with 3 C2s. Okay. These molecules are generally known as DN molecules. For DN, you need to have Cn and n number of C2s. Am I making sense here, folks?
Professor, I have a question.
Yes.
Okay, so you know how in the previous example you said for carbon H4, it was 4C3 and then in parentheses C-H?
That's a CH bond. Each CH bond direction is a C2 axis, yes.
Okay, so for this example you just did, would we have to write the
No. Yeah. Because, these lines are not along any one particular unique bond angle, right? If you look at this line, this contains two PTCl bonds, right? If you look at this C2, it does not have any PTCl bonds. It's not necessary to identify all of them. Okay. The reason I put the CH4, CH is to give you an idea about where those C2s are. Okay. Or C4s, C3s are. So, but maybe when we're talking about methane, let's go back to methane one more time and then see. We know there are C3s, right? Each CH bond is a C3. Does it have any C2? Here is your methane molecule. Does it have a C2?
No.
Yeah, intuitively speaking, you may think that it does not have it. But here is the trick. This molecule has 3 C2s, which are not conspicuously obvious. Okay, let's look at this. Hold the molecule like this and drill a line here. Look at my index finger here, right? My index finger now is a C2 because that will rotate the molecule and bring it exactly the same way. Indeed, it has 3 C2s. Let me give you a different way of looking at tetrahedral molecules. Although you have done a lot of tetrahedral molecules in organic chemistry, but there are certain tricks that we use in inorganic chemistry that throw more light into the shapes of molecules. So here is a tetrahedral molecule, right? You have 4 hydrogens and the carbon in the middle. If I were to take this molecule, put it in a cube, let's see what happens. That's a cube into which I'm inserting my methane molecule with the carbon in the middle of the cube. When I do that, what happens is I have 2 hydrogens here, 2 hydrogens there. Okay? So we can call the hydrogen 1, 2, 3, and 4. Now, if I were to draw a line that goes through the carbon, comes to the floor, comes back here. If I were to rotate this by 180 degrees, what do I get here? This will come here, that will go there. And because I'm rotating, this will come there, that will go there. And the resulting configuration is same. Am I making sense here, folks? So it has C2. So I drew one way. I can also draw another line here and draw another line. You can pretty much call it X, Y, and Z axis. Okay, this is Z axis, X axis, and Y axis. If you call the carbon as the origin and then draw X, Y, Z Cartesian coordinates, each X, Y, Z directions are synonymous with a C2. So this molecule has a C2. The question is, suppose if I were to replace one of the hydrogens with a chlorine, do I have a C2 now? No. You lose it. So CH3Cl does not have a C2, but it has only, does it have any C3? Remember in methane, we have 4 C3s, right? On the same way, if we look at CH3Cl, do we have C3s?
Yes, but there would only be 3.
3 or 1?
3.
3 C3s? No, because there is only one C3, the CCl bond, that will rotate these hydrogens. If you were to use the other CH bond, right, that will put the chlorine back here, hydrogen there, it does not look exactly the same. So going from methane to methylene chloride, CH3Cl, we lose 3 C3s. We only retain 1 C3. That C3 is along the CCl bond. The remaining CH bonds are not C3 axis anymore. and we also lose C2s. So that's why methane is more symmetric, because it has 4 C3s and 3 C2s. Amazing. But when you replace one of the hydrogens by chlorine, you get only 1 C3 and lose all your C2s. So this is how, as chemists, we try to talk about the symmetry. We say methane is more symmetric than CH3Cl. Am I making sense here, folks? Let's continue some more rotational acts of symmetry. Let's look at CO2. CO2, as you all know, is a linear molecule, right? Suppose if I ask you, what is the highest fold rotational axis of symmetry this molecule has? So in general, when I say highest fold rotational axis of symmetry, if a molecule has more than one rotational axis, then let's say if you look at BH3, right? It has C2s and C3s. So the highest fold rotational axis of symmetry is C3 because 3 is greater than 2. In the case of PTCl4, the highest fold rotational axis of symmetry is C4, although it has C2s. Okay. So on that basis, what is the highest fold rotational axis of symmetry the CO2 has?
Two.
Only C2? How many C2s we have?
Can you repeat that question?
How many C2s? You said C2 is the highest fold rotational axis of symmetry, right? Two-fold rotational axis. My question is, how many such C2s are there in this molecule?
Well, the double bonds can't like rotate or anything, right?
Oh, you can rotate anywhere you want, as long as the resulting configuration looks like a twin.
Are there 4 C2s?
More. See, here is a situation where you are both right and wrong. The reason why you are right is, yes, it has C2s. The reason you are wrong is C2 is not the highest fold rotational axis of symmetry this has. The linear molecules present a very special case. So let's imagine if we draw a line along this axis, right? What is the smallest angle that you need to rotate this molecule before you can assume look-alike configuration?
Well, you could rotate it by 1 degree and it would still look the same.
How about 0.1 degree? Point 0.1, okay. How about 0.001? How about 1 times 10 to the negative billion? Same, right? So what should be the value of n then?
Infinite?
Infinity. You are absolutely correct, sir. So this has a C infinity. All linear molecules have an infinite fold rotational axis of symmetry. If you look at hydrogen, simple, right? Single bond, linear molecule, that bond axis, that bond direction there, the HH bond here, is an infinite fold rotational axis of symmetry. So because by rotating it even by smallest fraction, the molecule does not suffer any shape change. Okay. Now, it has a C infinity. How about the C2s? Where are the C2s, folks? That's a C2, right? How about a line passing through C but perpendicular to the board? Is that a C2 too? Huh? In fact, you can have a circle around the carbon atom and draw any line. All of them are C2s. If you have a circle around the carbon atom, that circle being perpendicular to both the oxygen atoms, every line there is a C2. So how many C2s we have?
Is it infinite?
Infinity. Absolutely correct. So it has infinite C2s. So what is the group we should call this? Remember, if we have Cn and Nc2s, infinite number of C2s, what do we call that? D infinity, right? This is a D infinity group, very symmetric. How about something like oxygen? Linear. What's the highest fold rotation axis of symmetry on this molecule?
Infinity?
Infinity. You're absolutely correct. That's C infinity. That is along the double bond axis, right? Right here. That's your C infinity. And does it have C2s? The only difference between oxygen and carbon dioxide is, in the case of carbon dioxide, carbon is in the middle. But this axis, there is nothing in the middle. So the point that is the midway between the both oxygen atoms, although there are no atoms here, but you can have an imaginary line here, and you can have infinite number of C2s. So oxygen, O2, and CO2, both are D infinity groups, right? Is CO2 polar or non-polar?
Non-polar.
And how about O2, polar or non-polar?
Non-polar.
Non-polar.
Great. So now you see a connection. A molecule not having polarity and having a D infinity group. Remember, I was telling you how symmetry can help you to figure out the properties of molecules without having to test them. Let me give you another example. Linear molecule, HCN. What is that axis there? Is that a rotational axis of symmetry or no? Yeah? What should be the order of rotation there?
Infinity?
Infinity. Looks like CO2, right? But there's a small difference here. Does it have a C2?
No.
If you were to rotate the molecule along this line, the nitrogen goes left, hydrogen goes to the right. That's not how the molecule is there to begin with. So it does not have no C2. Is HCN polar or non-polar?
Polar.
Polar, you're absolutely correct. So now you see the difference between non-polar molecules and polar molecules in terms of the presence or absence of symmetry elements. A molecule cannot be polar if it has C infinity and infinite number of C2s. It can be polar if it has C infinity, but no infinite number of C2s.
Can you repeat that one more time? That last thing you just said?
A molecule cannot be polar if it has a C infinity and infinite number of C2s. It can be polar if it has C infinity, but no C2. In this case, no C2, although there is C infinity.
What about like a water molecule? Because that's polar.
Water
But
is not linear, right?
they
Water is not linear molecule. A linear molecule cannot be polar if it has C2.
Professor,
Yes.
go down the middle with like the carbon. It's okay.
No, I'm sorry. I'll write it again. No problem. No big deal. I have done that a million times. Yes. Okay.
I'm just curious, if you go down the carbon, can it be C1 or does C1 not exist?
C1 is E, right?
Yeah.
So all molecules have C1. C1 is basically
Okay.
rotating a molecule by 360 degrees, which is doing nothing.
Yeah. Okay.
So, but the condition for polarity is not linked to C1, it is linked to C2.
Okay.
Am I making sense?
Yeah, that makes sense. Thank you.
Great, excellent, very good. Questions up to this point, folks? I think we've been doing so many examples. We looked at C1, C2, C3, C4, C infinities, right? And then we have seen molecules that have C3s and C2s, right? Like methane and BH3, both have C3s and C2s. We've seen molecules having more C3s and replacing the atoms with different atoms. We change the number of symmetry elements that it has. So all this is extremely important in terms of identifying the molecules. Okay. If a molecule has set of symmetry elements, right, its spectral properties are determined by the set of properties, not by the nature and identity of the atoms. That becomes very clear as we go through more and more examples. But at this time, I would like to see, can we move on to the next thing, which is called the plane of symmetry, reflection planes. You can practice, of course, you can read the books and you can go through several examples, websites. There's so much available. So let's talk about reflection planes, sigma. So a molecule is said to have a reflection plane if you draw a perpendicular from any atom in the molecule to the plane and extend it to the other side of the plane by the same distance. And if you encounter a similar atom, then we say it has a plane of symmetry. Let me give you some examples. Let's say we start with simple example of water. The reason I start with simple examples is something that you can relate yourself, okay? Because you've seen this. This is your water. Now, if I were to cut a plane that bisects the HOH bond, and so that's the plane I'm talking about. That plane contains only oxygen atom. The plane extends towards me and behind the board, and the hydrogen atoms are on both sides. So this is a reflection plane because if I draw a line from this hydrogen to the plane and extend it to the same distance to the other side, I get exactly the hydrogen atom. Same. And if I do the same operation for this hydrogen, I get the same thing. So we say this is a reflection plane. Am I making sense? Okay. Let's look at another molecule. if I look at a pyramidal molecule, NH3, does it have a reflection plane? Now I want you to watch my palm being the plane of reflection, and I'm bringing my palm and containing one of the NH bonds, right? Is my palm a plane of reflection then? Remember, if I put that
Yes.
one, right, that is those two hydrogens will be reflecting, right? So that is a sigma. And how about the second NH atom? Third, all three are reflection planes. So we say this molecule has 3 sigma. All right. I'm going to use a letter V. I'll come back to that. If I don't, ask me about it. I'm calling sigma V's. Let me do one more. Let's look at BH3. What's the highest fold rotational axis of symmetry this molecule has, folks? We did this example before.
It's 3, right?
C3. Now, would you agree that if I have to draw a line using one of the BH bonds perpendicular to the board, right? If I were to draw a plane that contains the BH bond, but the hydrogen atoms are on both sides of the plane, is that a reflection plane?
Yes.
Yep. How about this? Look at my hand here, the way it moves. That's a plane. Is that a plane of reflection?
Yes.
Yes. How about this one? Plane of reflection?
Yes.
So I have 3 sigma V's. Right? In addition, this is a planar molecule, right? Unlike ammonia, this is a planar molecule, which implies that all 4 atoms are in the same plane. Isn't that plane also a reflecting plane? Right? That's also a reflecting plane. All planar molecules have at least one plane, that's the molecular plane itself, is a sigma. So this is a sigma too. So it has 3 sigma V's, which are like this, and then the plane of the molecule, I call that sigma H. The H refers to horizontal plane of reflection. The V refers to vertical plane of reflection. What is the difference? Here is the clue. If a plane is perpendicular to the highest fold rotational axis of symmetry, if a plane is perpendicular to the highest fold rotational axis of symmetry, then that plane must be designated as sigma H. On the other hand, if a plane contains the highest fold rotational axis of symmetry, that plane is termed as vertical plane of reflection, sigma V. A plane either contains the highest fold rotational symmetry, or a plane is perpendicular to the highest fold rotational axis of symmetry. That is what qualifies V or H. Am I making sense? Let's go back to our familiar example of water. We already said water has one plane of reflection, right? Which is the plane perpendicular to the board containing the oxygen atom. Does it have an additional plane?
Yes.
Is water a planar molecule? Water is a planar molecule, right? Look at the water here. It's plane. If you have 3 points in space, they must belong to a plane. That's what mathematics tells me, right? If you have 3 points in space, 3 points constitute a plane. 3 nonlinear points, of course. These are 3 nonlinear points. So this must be a plane. So I have the plane of the molecule, that's also sigma. But is that sigma H or sigma V?
Sigma H.
So what is the highest full rotation axis of symmetry this molecule has? Water.
Two.
Remember, that's a C2, right? Is that perpendicular to the plane or is it in the plane?
Is it in the plane?
Absolutely. So whether you take this plane or the plane of the molecule, both are vertical planes of symmetry, no horizontal plane of symmetry in this molecule. A molecular plane can be sigma H only if it is perpendicular to the highest fold rotational axis of symmetry. I'll give you one more example. Let's talk about xenon tetrafluoride. Planar. What's the highest fold rotation axis of symmetry here? Some of you can unmute and tell me, at least if I know that you're learning something. We can be wrong. I have been wrong many times.
4.
4, you are absolutely correct. Where is that axis? Is that in the board or is it perpendicular to the board?
Perpendicular to the board.
So that's the axis, right? That's your C4. It also has 4 C2s, right? Remember we talked about this. Each FH is a xenon F. That is a C2. This is a C2. And the middle are also C2s. So there are 4 C2s and a C4. Good. Does it have a sigma H? In other words, if I look at the C4, right? The perpendicular to C4 is this molecular plane, correct? So this plane now is your sigma H. It meets that criteria. The criteria is any plane that is perpendicular to the highest fold rotational axis of symmetry is the horizontal plane of symmetry, sigma H. A molecule can have many sigma V's, but it will have only one sigma H. Because there will be only one highest fold axis of rotational symmetry, and there has to be only one plane. You can have many sigma V's, right? Okay. So it has a sigma H. How about this here? That's also a plane of reflection, right? If you draw a plane perpendicular containing F, X, E, X. So this is the plane I'm talking about, perpendicular to the board. That's a sigma H. I'm sorry, sigma V. And this is another sigma V. You also have 2 more reflection planes. So we have 4. Now I'm putting another one there. Sigma D. That is called the dihedral plane of reflection. So a dihedral plane is basically, if I have C2 here and a C2 there, And if I can have a plane bisecting the C2s, which is this plane I'm talking about, that plane is your sigma d. You know, they look very similar, sigma v's and sigma d's. But as you can see, sigma v's contain more atoms, FXEF and FXEF. Those are the sigma v's. And the sigma d's contain only xenon atom, or the central point. So I'm talking about a plane that comes above the board containing only xenon. Those two planes are basically called sigma d's, or the dihedral planes of reflection.
And you have only 2 of those?
Two of those, because this is one here and one there. So I'm talking about a plane, right? Use that line and draw a plane normal to the board. Similarly, draw a line here and draw a plane normal to this board. Both have xenon atom, and when you do the operation around them, there are more atoms that shift. So that is called a dihedral plane of reflection. So we have horizontal planes, vertical planes, and dihedral planes of reflection. So given any molecule, you should be able to figure out and tell me how many sigma H they have, how many sigma V's, sigma D's, and so on and so forth. Let's look at another molecule. Methane. Right? How many reflection planes it has? Any quick answers from students? What's the highest fold rotation axial symmetry this has?
C3.
C3. Do we have a plane perpendicular to C3 that gives you reflections? C3 is along the bond axis, right? CH bond axis. If I were to draw a line or plane perpendicular to that line, do I have a reflection plane? No.
No.
So it does not have a sigma H. But how about sigma V's?
Would you have 3 sigma V's?
More. If you look at one carbon and 2 of the hydrogens, right? And take a plane, that plane is a reflection plane, correct? One carbon, 2 hydrogens, any 2 hydrogens and carbon. If you draw a plane containing 2 hydrogens and carbon, that will be a reflection plane because that reflects these 2 hydrogen atoms. So now, from a simple perspective of math, if I have 2, 3, 4, the condition is 3 of those atoms will be in plane and the remaining 2 will be out of the plane. So you can create a plane CH1, H2, CH1, H3, CH1, H4. Similarly, you can also create a plane of CH2, H3, CH2, H4, finally CH3, H4. How many planes we have? 1, 2, 3, 4, 5, 6. So tetrahedral molecules have 6 sigma V's. Am I making sense here, folks? All right, so I think we're getting close to a close time, but I'll try to upload something for the next Monday. In the meantime, I want you to get familiar with the 3-dimensional geometries It requires a little bit of imagination, and some models might help you. And on some of the websites, you also have three-dimensional pictures. So I'm not going to point anything because there's so many sites here. Some are good for some people, other people may benefit from other types of things. So I'll just leave it up to you. So if you Google the words, for you or YouTube, symmetry elements and symmetry operations, you have tons of them. They all teach you, but basically I gave you the pointers here. And I gave you a few examples. All right. So we'll meet again next Wednesday. We need to cover up some things. I'll try to do one for the Monday, and the next Wednesday we'll try to do what we call point group classifications on group theory, as well as identification of the point groups. Several of point groups are there, about 12 or 15 of them. So we need to go over some examples of those. And once the symmetry is done, I think we need to get into coordination complexes. A lot of stuff to do in this course. All right. So I wish you all a good time. Thank you for coming here. We'll be in touch. We'll upload this video. So if you want to watch it again 1 or 2 more times, please do so. We'll get that one sometime today. Okay, bye now.